Yo, 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 what's up? Let's do some scatter plots. So, if you watched the intro video, we talked a little bit about the basics of scatter plots, how you can describe them, some things about them, how you can find correlation. What we're going to do today is continue with that conversation, review a little bit of that, and then talk more about different things with correlation. So, um, here's an example I would like you to be able to do. It says each member of a small stats class ran a 40-yard sprint, and then they did a long jump with a running start. The table below shows the sprint time and the long jump distances. Okay, just to see if there's a connection between how fast you sprint and how far you go. So, create a scatter plot. Describe the relationship and find and interpret R, which is your correlation. You don't have to do that by hand. You can do that on the calculator. So here's what I want to just show you. If you want to pause this and try this on your own, great. But if you go to the calculator and you put all your stuff into stat edit, into list 1 and list 2, I've got that all in here. Hopefully I typed it in there right. I can find that scatter plot by going to second y equals. And on second y equals, here, I'll clear all this out so you can see. I have stat plot 1. I have it turned on. You can turn it on if you don't. I have it set to scatter plot. That's the first one. I'm using list 1 and list 2. I can change color on mine. Maybe you can't on yours. But to see that, I want to go to graph. I'm going to hit graph. Now, mine is already set here, but if yours is not set to work, you can hit zoom 9. Zoom 9 is zoom stat. That'll be working good for stats. It'll show whatever stat plot we want to show. And this is my scatter plot. Now, I can trace some things. I can see the different points here. It'll go around to the different points. I can go down, go back to my graph. I can see like parts of this graph. I don't have to actually go on individual points, but this is just moving my thing around on the graph. It's not very useful there, but I have a general graph that I can follow. Now, I'm going to put the graph here. And this is what it should look like with actual numbers, with actual labels. And I have the R. Now, you can see the same sort of thing. It is kind of going downward from left to right. Has a negative trend. And that gets us into how we would describe this. So, let's describe it. If I wanted to describe this, I would use DUFs. Okay, if you haven't done that already, go ahead and do that. DUFs. DUFs is describing a scatter plot, and DUFs again stands for direction, which is simply positive for up, negative for downward, or none if it's not going either. U stands for unusual features. Okay. That could be clusters or outliers. F. F stands for form. Basically, we just want to be able to state if it's linear or nonlinear. We're not going to deal with anything else right now, linear or nonlinear. And then S, the strength. We'll talk more about that later, but strength meaning, is it a strong correlation? Is it a weak correlation, or is it a moderate? All right, so I might describe this as the scatter plot comparing sprint times and long jump distance has a, I'll say moderate to strong negative linear relationship between the two things. So I have the direction being it's a negative. I'm saying that it's strong or moderate to strong, and I'm saying it's linear. and then I might state there are no clear outliers or clusters. Okay? So that's Duff's. That's how you make it. And then where we find that R, we'll get into that in just a little bit. Actually, you know what? Go back to the calculator. Um, briefly talked about this in the intro video as well. But if you want to go to some of the things that we're going to be doing stat calc, you can go to two variable stats to see all like the mean, the standard deviation of each list. I'm not going to use a frequency list, and I can see that. It does not give me a correlation, though. It gives me all this stuff about the x's. It gives me all this stuff about the y's, max and min. But if I go back to stat and over to calc, and I go down, we are dealing with linear regression. But I'm not going to do this ax plus b. That's like our y equals mx plus b. In stats, it is a little bit different. We're going to use 8. It's a plus bx. And we'll get into that later on. However, you can find the correlation from this. Now, if yours does not show the correlation, mine did not, I need to go to catalog. So second 0, I need to go down to D. So I'm going to go second that. Whoop. Go back to second catalog. Down to D. I need to find diagnostic. And I'm going to go to diagnostic on and run that. And then if I go back to stat calc 8, it'll give me my R. So it is a negative 0.8380 or so. All right, back to the lesson. Another thing we talked about last time. Variables, response versus explanatory. Explanatory variables are the ones that you can utilize to predict. Response is what comes from that. So kind of like your x versus your y. That's kind of the big thing there. So let's look at a couple examples of explanatory versus response variables. So in these two examples, identify the explanatory variable and the response variable for each of the following relationships, if possible. Explain your reasoning. So let's talk through these. First one, the weight in carats and the price in dollars for a sample of diamonds. Well, the weight is what helps predict the price. The price is the response. So this is your explanatory variable. The price would be your response variable. For that exact reason, weight helps explain the price. Okay, how about the SAT math score and the SAT evidence-based reading and writing score for sample of students? Does one predict the other? I would say either they're both explanatory or neither. Because sometimes the higher you score in a math, maybe the higher you score in the reading, but sometimes it doesn't. It could be vice versa as well. So this one's a questionable one. One more. Here's an example. The study of the effect of alcohol on body temperature. To study the effect of alcohol on body temperature, researchers gave several different amounts of alcohol to mice. Sounds terrible, I know. Then they measured the change in each mouse's body temperature 15 minutes later. So, explanatory versus response. The explanatory variable is what they're using. This would be the amount of alcohol. And because they gave several different amounts, the response would be the change in body temperature. After 15 minutes. Now, I wanted to point this one out because it is important to be specific. So students might be asked to do this, like on a FRQ or something on the AP exam, and they might just state alcohol as the explanatory variable. That's not enough. What does that mean? The type of alcohol? The color of alcohol? It's the amount of alcohol. You need to be complete in saying what we're dealing with. So a variable should have values that are capable of varying. In this case, it is the amount. So alcohol is not enough. So just a point of emphasis there with the AP exam. All right. In a lot of the studies that we're dealing with, we want to be able to show that changes in one or more of those explanatory variables does actually cause a change in the response. However, it doesn't always mean causation. Correlation does not always mean causation. And we're going to get into that a little bit later. But here's one example. This definitely looks like there's correlation. Revenue from skiing compared to the number of deaths from being tangled. Yeah, comparing those. Perfect. There's a strong correlation, right? No. Sure, there's correlation, but there's no causation. The more people ski does not mean that there's going to be more deaths by tangling. There's some other reason why there might be some connection there. So correlation does not always mean causation. But back to correlation. This formula is on your formula sheet. It's important to know. In the intro video, we talked about how to use it. Just a reminder that this is essentially your, that was a terrible little bracket. I'm going to clear that. A little bit better. This is the z-score of the x's. This is the z-score of the y's. Oh, I'm missing a letter here. So basically what we're doing is we're finding the average of the z-scores multiplied together, the average product of the z-scores. We can look at some different connections here to why this is positive, negative, or no correlation. And it really does have to do with like how things are related to the mean of each the x and the y. But we're not going to spend time on that for right now. Instead, I want to just look at a couple other things related to correlation. So first of all, it's important to note that correlation is always between -1 and 1. It can never be bigger than 1. It can never be less than -1. And it's always sometime between those. It could be 0. There could be no correlation. So this is an example of a correlation of 1, perfect line. Correlation of -1, perfect line. One note that I've seen on multiple choice questions on the AP exam could be saying find the missing coordinate. Like find a missing coordinate. It could be x or y or both. To make r equal to 1 or -1. So if you want a perfect correlation, you have to find that missing value. So for instance, we might have this, we might have this perfect thing. They might say, what is this coordinate going to be? Okay? So I would find the equation of the line, use x and y to find it. And we're going to get into that in a more detailed fashion coming up. All right, more about correlation. We've talked about strength, how strong correlation is. So in general, and we're going to talk about strength, it is part of Duff's. If you have a correlation or the absolute value of a correlation between 0.75 and 1, that's typically a strong correlation. Between 0.4 and 0.6 is considered moderate. And between 0.2 and 0.3 is called weak. Now, anything below that is almost nothing or very weak. Anything between it, you could say moderate weak, you could say moderately strong. Okay? So we can do the in-betweens there. But here's some examples of correlation. And it can look different to you depending on what the axes are labeled as, which is why we have this value that's called correlation. This is a correlation of 0 because there is really no connection. We can't see if there's a positive or negative linear. It's actually have a correlation of 0. This one has a little bit of something. It is going downward a little bit in this trend. Very weak, though, at negative 0.3. This one's a little bit stronger, but considered moderate. You can see it's positive. We've got a couple other ones here getting a little bit tighter. So this is an example of a negative one that's a little bit stronger. So you can say that's a strong, and this is a very strong one, but it's positive. And this is, again, so tight that it's almost close to 1. It's almost a straight line. Those are very strong correlations. All right. Now, a couple notes that we're going to get into next time. For sets of data, R, so your correlation and a slope of a line, should have the same sign. Should be positive if it's a positive slope, negative correlation if it's a negative slope, but they don't have to be the same number. They do not have to be the same number. There's one exception where this would be a zero slope, and it would be a zero correlation technically because it's a flat line. If you want to do some things with switching the units or switching the axes, that also does not really affect it. It shouldn't be any different. So like switching X and Y axis around, it shouldn't matter. The correlation will stay the same. We'll talk more about that next time as well. If you switch units from feet to inches, still should not affect the correlation. Correlation does not have a unit. It is just a measure of essentially how tight the data is. And since we're dealing with these standardized scores, it won't affect the correlation. But something I said we're going to talk about a little bit more is correlation and causation. Correlation does not mean causation. So just because you have a strong linear relationship does not mean that it actually has that cause and effect. Another example that I have for you is ice cream sales and drownings. If you want to think about it, anytime ice cream sales increases, the number of drownings generally increases. Did you know that? It's going to be some sort of a scatter plot like this. You could flip those X and Y's around, it'll be the same deal. If you have more drownings, you'll have more ice cream sales. That's not because they are causing one another. That is because there's some other thing causing that, and that's called a confounding variable. A confounding variable in an experiment is a variable that is related to the explanatory variable and influences the response variable, and may cause a false perception of the association between or the correlation or causation between the two. So in this case, what is the confounding variable? It is the weather. Weather is the confounding variable. If you have higher temperature, you happen to have more ice cream sales. And you also happen to have more drownings because there's more swimming. And there's that drownings. So it all was actually caused by the temperature increase. So that is a confounding variable, something that is not talked about but might be the actual reason. Now, on the flip side, just because you have a weak association or correlation doesn't mean that there isn't actually some sort of a strong linear relationship or nonlinear relationship. There still could be a strong relationship. Like you could have, if you're comparing, like looking at an IRA, so this is money talk, like retirement savings, but let's just say we have this, over time your money is increasing, but it might be slowly increasing, and then it starts to gradually increase more. Now, if I'm looking at that, that seems like there's a strong relationship. It's just nonlinear. So maybe the correlation isn't real strong. Maybe the correlation is 0.4 because it's nonlinear. So that's another thing we're going to get into in this chapter, how we can use nonlinear relationships in comparing. Okay. Now, one other note about correlation. Using average data can yield inflated correlation. So averages instead of actual individual data. Here's what I mean. Let's say you're talking about comparing median family income to mean ACT score, okay, by towns, okay? And in general, it seems like the higher the family income in towns, the higher the average ACT score. But again, those are averages. Those are not individuals, because in reality, if you look at individuals, you will have a lot of people who have low income, low ACT scores, but you also might have people with high income and high ACT scores. It might look something like this. But you might have those families with high income and their kids still have low ACT scores, but there are some with high income and some high ACT scores. And then there's everything in between. So guess what? There's really no correlation here. So using averages sometimes make something seem more related than it actually is. So just a note there. So I have all these different notes about correlation. So let's recap them. What do we know about correlation so far? If you don't have these written down, you might want to add them. Correlation doesn't imply causation. We've talked about that a few times now. Correlation does not measure form, okay? It measures how tight something is, essentially, how related something is. Correlation should only be used to describe linear relationships. It doesn't work with nonlinear, so we're going to talk about ways to get around that. Correlation is not a resistant measure of strength. It is affected by outliers. A couple other things. It requires both variables to be quantitative. So we have two numeric variables. Correlation makes no distinction between explanatory and response. Doesn't matter if you flip the x and the y around. It'll still be the same correlation. Correlation does not change when we change the units of measurement for x or y. If we change units, it'll still remain the same strength. And the correlation has no unit of measurement. It's just a number that relates, that gives a number to a relationship between two variables. So that kind of covers a lot of what we talked about today. I know there's a lot about correlation and a little review of some other stuff related to scatter plots. But hopefully at this point you feel a little bit more informed about what correlation is, also known as R. See you next time.